Okay. Hi, welcome to the second talk in the ENG webinar series. In this talk, we have Abhay Ratnaparkhi, who is going to talk about the concept of neural information processing. So, Abhay, over to you to discuss the concept.
Okay, thanks, Dinesh. So let me share my screen, and are you able to see my screen?
Yes, we can see your screen.
Okay, so today what I'm going to talk on, like how we can, what's happening in the information retrieval field, basically most related to the textual information retrieval and how we can leverage machine learning and what's neural information retrieval is, which is a state of the art related to the information retrieval systems. So let me start with the outline. What's going to cover? We'll start with some of the examples of information retrieval, which is some really basic things, and what will cover like what's the current state, like most of the information retrieval systems, how those are being developed. We'll take some example like for some of the retrieval systems that we work on within IBM, just from the perspective, and then we'll talk about the neural information retrieval and other happening things in the area. Okay, so let me go to the next slide. So what's document retrieval? Generally, this is a kind of the document retrieval and ranking has been there since, yeah, since decades. Like we have the web search engines like Google, Bing, and others providing the search over a whole web data. We have open source solution in this space, which provides you the ability to develop some kind of a solutions for your enterprise based out of a same kind of a technology related to the retrieving and ranking. The Lucene is one of the core open source project in this field. And the third thing is we do have like the products and from various uh, market leaders and various companies are providing these products to develop such kind of solutions. They call it as a insight engines, which does something more than the just information retrieval, but providing some insights towards your data. So yeah, there is a good market over there, good open source support, but the traditionally the if you see them as a kind of a search engine, the architecture is the same. You have a data that has been like indexed by using some kind of document representations. So you get your data by using different means, and then you analyze your data. Like if you have a data for some language, you will analyze it maybe differently, so depends on your content and language. There are kind of analyzer pipelines, and then you make it available for indexing. You And what indexing means is like you just put it into the format which is better for the retrieval, and there is a kind of a ranking procedures, where you have a query and you start with the query, and then you maybe get some query representation based out of, you can use, yeah, there are like many techniques to use, make your query expanded into the form, like use some synonyms and acronyms, all those things, and make sure that you have a better query representation, and then use some, get the results from your index, use some ranking procedures, and get the results. So this is a search engine or the information retrieval since decades. What There are like multiple tasks, like at the time of indexing you have to do some content extraction, analysis, the links, how they are like linked with each other, how the documents are linked, get some documents related features, enhance your content to the better content. So a lot of these tasks still like are using some kind of a machine learning techniques. Like one popular example is getting the text from the HTML. The state of the art like approaches over there all uses some kind of neural network model to extract the proper text from the HTML. So yeah, so content deduplication, deduplicating your content. So yeah, many sub tasks have some kind of a there are what I mean to say is the information retrieval as well as the machine learning. These two fields grown like simultaneously, and a lot of approaches being used in the information retrieval for these different processes. On the ranking side, you can see like learning to rank is a one kind of a special area where many models or many different techniques have been developed, uh, where you can apply some machine learning for the ranking purpose, how you can rank your documents so that the relevant documents come on the top side. uh, yeah, so let's go into this is a kind of a traditional retrieval system, and we mentioned about the inverted index. Basically what happens is whenever you have a text, you convert it into the format, like for each word in the text you get the list of documents where those text appears, or where that term appears. So if you have a term like a Watson IBM discovery, you will get the list of documents here. And then at the time of, and this is a kind of a simplest form, we can it as an inverted index, because you inverted your documents from term to list of documents where the term is appearing. And then you apply some kind of ranking over this, because your query contains the terms. So you will, let's say if my query is what's an IBM discovery, I will find out, just do like find out the common documents from this posting list, and then gives and rank them based out of some kind of a ranking function. So popular ranking functions, like kind of a default ranking, still in lots of like open source, wherever you see this Lucene and all, they use these ranking functions. The popular one is BM25, some kind of a probabilistic ranking based out of the term frequency and inverse document frequency, and then you get some rank results. And as I this is we are calling it as a traditional search because it's been there, it's been like being used. And after the ranking, there is, as I told you, some kind of a machine learning based re-ranking, and we will see that the learning to rank procedures, but that's what been applied here, and you get the results. What's the shift going on is, rather than having some retrieving and ranking pipeline where you have your content and you make your index, and then on that index you put a query, is it possible to just have some kind of a machine learning model, given a query it will give you the results? So this is a kind of a shift in thinking, and there are like some good papers. I have listed them on the at the end, maybe about the notes, but which tells about why this shift at this moment, because at this point in time we have like a very large set of models which are capable of doing these tasks, and not only the ranking or the getting the search results, but many other tasks in the same model can do the multiple tasks, like answering the questions, maybe giving generating some kind of text out of, let's say, your query, maybe the relevant text which is not there into any document. So these models are doing some has a kind of a good capability. They learn over like a large text, and is we'll see what's happening in this kind of a shift. But before that, let's look into some kind of a real world example with the current traditional search approach. And feel free to like ask or bug me anytime in between. Yeah, so that's what the first use case we saw, as a information retrieval. We call it as a search, the textual search. We call it zero shot learning, where you have a query and get the results and rank them. The another use case is question answering, right? And you have seen like the IBM Watson in 2011 has a system called Deep QA, and that's based out of some many NLP techniques used in the Deep QA. But the crux here is all those NLP techniques used that times are based out of, let's say, the primary thing is you have to do some primary search, get some candidate answers, and then you use multiple evidence sources to score the candidate answers. Like you have a question and then you will generate multiple set of answers and then try to score them based out of some kind of a machine learning technique and get the best possible final answer. uh, and yeah, all the NLP techniques are used are based out of, not really based out of all the deep learning approaches, but if you see what's the state of the art, is the GPT, or the if you have seen the chat GPT, what people have tried, like the kind of a questions where Watson Deep QA has failed in 2011, in 2022 or 2023, the GPT based kind of a systems, or the we call it as a deep learning based architectures based out of a transformer, and those systems has outperformed, and those were able to answer like where the Watson has failed. So why is that happening? We'll see like what's the current state of the models, and we call them the language models, because they are trained over a large set of corpus, uh, and those are like a deep learning based models. All this evolution starts with the BERT, which is a which came up in like 2017 as a transformer model. So the basically the transformer model is a kind of a deep learning architecture where you learn from a sequence. So you have a set the sequence that is an input and you get the sequence as an output. Maybe the popular example is like the language translation. So if you have to translate one language from the other, these transformer models are like the state of the art kind of performance over there. Like you give the transformer as input, you learn like uh, this language model over the large set of data, and then you have those weights, those you gather over the time, which you can, and this is learned once, and then you can reuse it. Like if you have a learned model over the last test large corpus, you can then fine tune it for your domain to do some specific task. So what's the kind of benefit of using this? Like they are suitable for multiple applications, not the single one. So you can use BERT for, let's say, sentiment analysis, text classification, question answering. The same model, you can tune it for different tasks. That's one of the big thing, and you can see over the time the size of these models, like the number of parameters on which it's getting trained is increasing. So many player here, and I think over each every week there is something happening in this field where the large language models are coming up. People are training a big language models, and there are like people are seeing some kind of benefits of getting to the larger models. Like you're able to get synthesis, and now you can see the synthesized content is at par the human level with these larger models. You can ask them to write an essay, and this is all in the text field. The same thing is happening from the images and other sites, where you can create a paintings by some artist. You can just ask the model to give me a painting, and it will generate nearly the same paintings that artist might have done. So they have a capability of generation. They can generate different things. You can ask them to write essays, but generation is the best capability, but you can fine tune it for the different tasks. That's another capability. We will see some of these aspects in the uh, like information retrieval related to the search engine, how those models we are using. Okay.
I can ask a question here on the previous large model. So languages like ChatGPT, which are systems like chat and conversation bot, do they just use a pre-trained language model, or is the pre-trained language model just a component in multiple other components they have to build to use the solution?
Yeah, so the chat GPT is that's a good question. It's just a component for them, but I will say it's a kind of a major component. Like the GPT, which is more popular, it uses the GPT 3.5 as a backend component, but it involves much more than that because it's a chatbot, right? So it's not only what GPT can does is given a sequence, it will give you the sequence, maybe other sequence out. So it has a generation capability. You can give a sequence as some kind of a question, and it will give you some other sequence as an answer. So that generation capability, but they have fine-tuned it for different tasks and identifying those tasks. So there is a lot more than that to identify what's being asked. Maybe sometimes the question is being asked is a mathematical in nature, so they have to go through the different route to answer it. But yeah, the GPT's model is one of the main component in these kind of a chatbots. But it's not only the model. It's overall, yeah, they have many things over it.
Okay, great. Thank you.
Okay. Okay, now let's discuss, means again I'm coming back to the normal search, the enterprise search, or how the search use cases are, what kind of a things needs to take into the account while developing the search solutions. And again, this is with mostly the traditional stack, because that is still like a predominant. And to see, so whenever you are developing the search engine solutions or the search solutions for the enterprises, what the first thing is, I will say you have to start is the user experience, like what exactly the users would like to see as a search results. So if you see for the IBM.com, the search results, mostly users are interested in knowing, let's say if they are coming to the IBM.com site and doing some search, they wanted to know like what kind of a products, maybe products are there, what kind of a support issues related to the product. They might be looking for downloading some kind of a product. So you can see you have to develop your user interface by looking into that, the information that you have that taking into that account. The same thing if you go to the IBM internal search, you have to look for, let's say people are coming here for looking for the people or the tools or some other aspect. So this may be the ultimate aim of any search solution, is to make users happy when they try to query something and get them the relevant results as fast as possible. So the user experience and design is a key for doing that. Apart from that, what you need to do is identify the sources, do some kind of a crawling, or some other approaches like getting the data in. There could be n number of approaches, and I will say like 70 to 80% of the time is spent on getting the data, because getting and curating the data is one of the major challenge in any kind of a end-to-end search system. And whenever you have that, what you do is you index that data, as I told, like normal indexing solution. And maybe you can create a different formats, like you can create some knowledge bases or some kind of a knowledge graphs out of it, so that you can answer different types of queries. Or you may have some federated sources where you can getting the data, like querying them directly. But the main thing is you get the index out of it. Inverted index still like a popular, so you create an inverted index. And we will look into this week is the vector search kind of a thing, where you can create a different form of index called as a, which is suitable for converting your document into some form of vector, and maybe doing some vector search over that. We will see that, and that's a part of some kind of a neural retrieval that we'll be looking into. But whenever the query comes, you will do a kind of a search over it. You merge them, those results together, and then you do some kind of a re-ranking, as I told, like one of the some machine learning techniques to re-rank, let's say top n documents. You can't like rank all the documents, because these are like compute intensive kind of a thing. So you have to work on some subset first, retrieve as much as possible, and then rank, let's say top 100 or top 1000 documents, and then give the rank results to the users. So this is one of the search architecture. And let me go and let's discuss the learning to rank. So this is a supervised machine learning techniques, and there are many models, many different techniques that are used for ranking. But all they have the some set of ground truth. Like you start with some set of ground truth, like you have some results which you know, for this query these are the good results and these are the bad results. So mostly you start with some ground truth. How you know that ground truth? Maybe you have some best experts who give those labels for the documents, and here the task is ranking. It's not general classification in between two classes. It's like you given a query, you have to rank the results. So what you can do is, one of the way to do it, given a query, you can say this document has most relevant document, this is a less relevant, this is not at all relevant, maybe some kind of a labeling for query and documents. And you have those annotations generated, and you train some kind of a supervised learning model, so that you can have a proper ranking of the document. But in this scenario, doing those annotations is human labeling is very challenging task. So there is another approach that generally the search systems use. They have the search UI. Generally people, the users go to the search engine result page, your search UI page, and they try to click on different documents. So in general, like there is what clicks are happening gives some indications about the what's the relevance of the query to the document. So give you an example. If no clicks are happening for a query, it means like user, by looking into the search engine result page, user found that there is no relevant document and might have like gone like from that search engine result page, or modified his query maybe to find out more relevant documents. So you have to gauge like user behavior, user analysis, what's user is doing with the search engine result page, and based out of that you can combine these signals from many users for many queries, and then you can devise like you can get this ground truth data for which is useful for the ranking. So if you have some documents which is being, let's say, which is ranked on, let's say, rank 9, but being clicked by many users multiple times, it means that ranked document is still very relevant, and maybe your machine learning model can re-rank it so that in future it will be ranked little higher than that. So there is a field which deals with user behavior analytics based out of their clicks, called as a click model. Many mathematical models has been proposed, and yeah, still like there are some things, many evolutionary models comes, but the click models is basically analyzing the user behavior of the clicks and generate the relevancy matrix, which is used by the re-ranking. And in the ranking procedures, the mostly the relevancy matrix, you can use precision recall kind of a matrix whenever you have a task as a classification. But here the NDCG is one of the um, major matrix that's being used, which is basically used for, tells that this ranking is better than this ranking. So basically two lists of ranking, how you can measure which one is better. So that's given you by the NDCG. We are not going in detail to that, but just to give you like there are many ranking models proposed, but in general it looks like this. For a query, you have list of documents, you have these relevancy labels, either human annotated, or you have these labels which you generated from your click models, and then you have a list of features. This is a pretty long list of features, but you can see the what's the score of your the document that has been written by your, let's say, lexical engine. um, Maybe the score of just the one field like title, what's the page rank score of your document, how many visits are happening to this if you have that in your record, and maybe many other fields. But with this data you train your re-ranker using some kind of ranking models that are there. Like there are many re-ranking procedures, but that's how like you re-rank your documents, get the and rank them to get the proper search results. So this is one of the field like learning to rank, where machine learning is being used by the search engine for ranking. So yeah, uh, let's go to some I will, maybe I will just quickly talk about this. This is not related to the information retrieval, but this is related to generating, like making, while you are developing any kind of a machine learning application, what are the, like, some of the important things that you can use. One of them is feature store. So as I told you, for this kind of a machine learning based ranking, you have to store all the features and everything, right? So the feature store is one kind of are getting popular nowadays, where you can get some life cycle to your features. Like, let's say if I have a feature called as a uh, document score, let's say, or the here you have seen the feature as a page rank. Maybe that is one of the feature, or number of visits. These features information comes from the different sources. Like, there is no like one source of the features. Let's take an example of fraud detection use case, where the feature can be coming from, let's say, um, what's user action or user IPs, last IPs, maybe that's coming from different sources, and some other information coming from different sources. So there is always a flow of information coming in. um, so your features value changes over the time. So it's basically is a time series kind of a things. If you define a feature, its value changes over the time. Not all the features has same leniency or same, they have a different values at different times. So you need some kind of a store, we'll say kind of a data store, where you can define your feature, and maybe over the time, insert the data into those feature store, and make those data useful at the time of prediction. So that's why the feature stores are important. So you can start with, like, there are many open source feature store implementations getting popular nowadays. Feast is one of them, but that's being used. Like, you can define your features, your data engineers define the features, or the machine learning engineers work with that, and maybe on the production use the same feature store to retrieve the feature values. So basically all the supervised learning kind of a models make use of this feature store as a repository of storing, modifying, and uh, getting the data from the feature store. uh, Again, uh, yeah, so you can see, in generally the feature store has this ability of like offline feature store. uh, Feast is one of the prominent open source feature store, getting popular, has been integrated with many cloud services and many other repositories. And what general architecture is, you have a lot of data which you store. Let's say for some features you store for a long lineage, let's say last year of data into the feature store, and that's where you use some kind of offline feature store. You get you put your features related information into that offline feature store, and then you materialize it so that it's available at the real time inference. So that's called as an online feature store. And all this capability has been provided by the feature store. You have some kind of offline, let's say you use object storage for offline feature store, because there is a lot of historical data associated with the feature. Then you have some kind of a materialization that's over that offline feature store, that actually gets the recent value of every feature into your some past surveyable online feature store, and your service uses that. So these kind of a systems makes like your features reproducible. And let's say I want to see why my system has ranked this document at this time in this way. uh, what we can I can go is I can go into the same system and see what were the features available at that time. Like, my offline feature store has all the leniency of the features, so I can go there and see what were the features value at that time, and maybe that will help me to analyze how the data is being used. So feature stores is one of the thing that you can use while developing many machine learning systems. Um, and the another one is the version control for machine learning. It's the same way, you have the GitHub for code. You can use version control systems where you can put your models data into some kind of other formats or other backends, and just make use of the small files just to represent those models, like make the hash of them and put it into your source control, and just tag it with your source control, so that you can reproduce whatever your system state at some point in time. So feature store and DVC both help us you to reproducible experiments, go to the state where your system was, and yeah, much helpful in like developing any kind of a machine learning systems. Okay, I will just skip this, but this is a kind of a another use case. I will skip this one, and word embeddings. That's something uh, is related to um, the neural information retrieval. So they start with like word embeddings, means given a word. Generally, you have seen like in the traditional search for the word, you get the posting list where the list of documents has been um, list of documents with the word. But is it possible to represent a word into a kind of a distributed representation? And that's called as a local representation. Let's say you have, let's say, these 10 words in your corpus, and this local representation just tells make like one word as on and all other off. So maybe this is called as a one hot encoding, where you just have like represent with a sparse vector where just one vector is set and all other bits are not set. So this is a local representation which involves, let's say your whole language has, let's say, uh, 10,000 words, then your vector is 10,000 long for each and every word. So this the other shift over is can we represent is in a distributed way, like can we represent the same word with some set of like a smaller vector, and with, let's say, the word banana, can we represent it with, let's say, it's a fruit and it can elongated fruit. So yeah, we can have a distributed representation for the word, and it starts with some kind of a models like word to vec, converting the words into the vectors, and that gives rise to, as I told, like pre-trained transformers and all. Again, those you can use like a BERT and GPT-3. Those also gives you the some vector representation of the word as well as the sentence and documents. So whenever you have the vector representation, it gives you some more you can do some mathematical operations to get process the information. And let's look into this neural information retrieval thing. We start with the idea behind neural IR is use any kind of a neural network to which that will help us like a shallow or deep neural networks for the information retrieval task. And we have seen the learning to rank is one of the thing where you can use a supervised learning approaches, and in supervised learning approaches you can use many different deep neural networks just for ranking if you have a ground truth data. But that's still like a kind of a legacy systems. Let's look into what's happening here. Is one kind of architectures that coming prominently is a representation focused architecture, where you can see you have this neural network. Given a query, you represent query into the vector, some kind of a vector form, like a mathematical vector, by using some neural network architecture. Most prominent here is the encoder decoder kind of deep neural architectures, like whatever the BERT uses. The same way you convert your query into the vector representation, you convert your document into the vector representation, and as you have both as a vector, you need to get some kind of a cosine similarity or dot product of this vector to see how relevant your query with your document is. So this is these there are many models coming up with this, where uh, you use these kind of a pre-trained transformers which are available, which have been trained on large corpus. Those transformers have a capability of uh, giving a representation, vector representation of your query as well as documents data. So use a vector representation from those models and use them or fine tune them for your use case, and then use them for finding the similar documents. So this is called as a dense vector retrieval, where you convert your documents into the dense vectors, which are the small, let's say the vector size is small, and then you will do some kind of a point functions to aggregate the results. The another types of neural architectures that's getting prominent or that are there is wherever you use like the query and document, you train them together, like the neural network model, you train them together and then you use the trained weights. These are called like cross encoder models. So this, the first one is called a bi-encoder, second one is a cross encoder, but both are the encoder decoder neural network architectures. The second one are like costly, time consuming. That's why those are being used into the re-ranking phase only. The first one is are getting popular, and that's where we call it as a vector search. So you convert a document into the vector and do a search over the vectors. So basically you have all these documents converted into the vector and then given a query, then you will find out the nearest neighbors. So ultimately problem boils down to finding out the nearest neighbor for that vector. And there are many ANN kind of a search engines which gives you the ability to store these vector representations generated from any kind of a different transformer models, and then gives you ability to retrieve the nearest neighbors to that vector. Again, this is a kind of a growing field where, because you have so many documents, you cannot calculate like for all the vector distances to get the closest vector. So you have to do some kind of approximations. So the field that comes into the place doing the approximate nearest neighbor search. So we call it as an ANN search. For the ANN, there are multiple different ways to represent these vectors into the format that at the time of retrieval, you can retrieve them much faster. You can get the closer vectors much faster. So these are called the vector search engines. So some kind of open source vector search engines come into the picture like Milvus, Waviate. Those are the open source vector search engines. Then, yeah, let's not go into the detail of approximate nearest neighbors, but there are like, just a point here is doing approximation is the key, because you cannot real time get all the distances for all the vectors. So there are many techniques that come for doing approximations into the literature. But the final thing is, can we, yeah, another thing to think on this line is what else we can do. I haven't listed some of the things, but these vector search engines are basically much more useful, where like they are useful for semantic searching. Like what happens, traditional search engines, you have a query, the exact term needs to be there into the document to get your document retrieved. So for the semantic search engines or the vector search engines, as you have some abstract level representation of your query and data, you don't your retrieved documents are just semantically similar, so you don't need to have like the exact documents. That's one of the bigger advantage of the semantic search engines. Again, these are very helpful in the case of images also, because images always have there is a lot of abstractness into the images, and the representation of images into the vector is much more helpful at the time of retrieval. So you can see the search engine where you can provide the image as a query and get the related images as a result. All the technique behind is they mostly use the vector search, some kind of a vector search engines. Yeah, how we can some research directions here is how we can combine the vector search with the traditional lexical search, how we can combine those results. Maybe, yeah, I will say some kind of a things to look for is, can we use quantum computers to do, rather than doing approximations, can we use them uh, just to do kind of a do all this search in parallel, where you can get the not the approximate results but the exact vector search results. But yeah, there are many things happening in the vector search space. So okay, so let me skip this, and yeah, some of the challenges I will say it's data quality, bias in the data, model drift. But yeah, this is what I have for today's presentation. And maybe if we have any questions, I will take those now.
Thank you, Abhay. Thanks for the talk. Any questions from the audience?
So does Watson Discovery work on a model search type method or a query, the standard query-based method?
Uh, yeah, so the Watson discovery is predominantly a standard query based uh, because it uses the on the back end it uses elastic search query retrieval, but it has also supports for this vector searching, means being like the latest uh, thing has this vector thing included, but it mostly, I will say, it goes with the traditional search, but on top of it a lot of other natural language processing things.
Thank you.
Abhay, one question was, are there particular domains or particular areas in which machine learning or vector search is better? And are there areas in which the traditional query-based approach works better? Any ideas on which works better in which condition?
The vector search works better surely for images and all, like audios, images, and other MIME types than the text. For the text, till like I will say last 2 months, all the there is a kind of a leaderboard for the text retrieval, like which is called as a benchmarking. Uh, it's called as a BEIR benchmark, the benchmark in information retrieval for different tasks. The nowadays, like since last few months, all the models that are coming up on the top, like few months before, the top model was a kind of a lexical search using BM25 ranking for the text retrieval, but I think the scenario has changed recently, and a lot of other these deep neural network models has achieved they are on the top list now. They are started outperforming in the text retrieval also. So I will say in the text also, it's not no more the lexical retrieval on the top. It's some kind of a combination of lexical, semantic, and other technologies. Means it's not only these two. There are some other things on the top of this where people are trying to do uh, combining this both, and maybe
Okay,
it's called, yeah.
okay, great. Thank you. Um, any other questions from the colleagues? Okay. So if not, thank you, Abhay. Thanks for this interesting talk. It's quite timely given all the interest in search and queries that's happening out in the industry. Thank you so much.
Super cool. Super cool.